Greetings of the day. We are from MITS. Myself, Thangarasan. I am Assistant Professor from the Department of Computer Science Engineering. Today, we are going to check a topic about the AVL trees concepts and the applications. Okay, so it comes under the category of data structures and algorithms. So first, we will just check what is data. So data structures is a way of arranging and organizing the data. Algorithm can be used for step-by-step process how to perform the actions towards the data edges. So under the data edges, we are having so many kind of the concepts. First, we will see what are all the categories of the data edges. There is two categories of data edges. One can be considered as a linear data edge, another one can be considered as a non-linear data edges. In linear data structures, the data will be arranged in some kind of the sequential form. In some kind of the order, it will be arranged. But in non-linear data edges, it won't be in any kind of the sequential form, which means we can't able to see in any kind of the linear order. So examples of the linear data edges we can able to consider as a array, stack and a linked list. And examples of the non-linear data edges we can able to consider as a trees and the graphs. Trees, while going for considering the trees on kind of the data edge, it contains nodes and edges. It will be like in the shape of the trees only. So it is used for arranging the data, and it can be used for arranging the connecting the node with one node to the another kind of node. That is, a kind of the data can be connected to one data to another kind of the data, and we can able to understand with the help of the trees what is the relation between the one data and the another kind of the data. So here there is so many kind of the types of the trees are there. Some of the trees are binary tree, binary search tree, AVL tree, B tree, red black tree. So likewise, so many kind of the trees are there. So today we are going to see about the AVL tree. So AVL tree, it can be expanded as Adelson, Walesky, Landis trees. These are all the authors name who are invented the AVL trees. Why we have went for the AVL tree means we have found some kind of difficulties with the binary search tree in case of the insertion and deletion operations. To overcome the whatever the hurdles we have seen in the before previous trees, we have went for the AVL tree. So with the AVL tree, it can be considered as a self-balanced binary search tree. So we have some kind of the hurdles in binary search tree, and we have some kind of the deviations in the binary search tree. To overcome those things only, we have came for the AVL tree. So here we can able to overcome whatever the things we have deviated in the binary search tree. Okay. So this is the, so that's why it can be considered as a self-balanced binary search tree. Very important operations about the AVL tree can be considered as a balance factor, which means it contains one kind of the formula, that is BF equal to height of left subtree minus height of the right subtree. Whenever any kind of the insertion or deletion operations is happening in the tree, you have to calculate the height of the left one, then you have to calculate the height of the right one. It should be subtracted and from the left to right mode. Okay, so if the values we can able to attain can be considered as a 0, 1 or minus 1. Okay, if we are getting the values 0, 1 and -1, it can be considered as a good balance factor, which means the tree is in some kind of the balanced mode. If we are not getting these values, we are getting more than that any kind of the values like 2 or -2, 3 or more than -3 or more than any kind of the value, then it can be considered there is no kind of the balance factor is available. We have to perform some kind of the rotations. Now we will check what are all the major operations we can able to do in the AVL tree. In previous also, generally in all kind of the trees, we can able to perform some major operations. One can be considered as the insertion, another one can be considered as a deletion, another one we can able to consider as a searching operation. Same thing we can able to perform here. Along with that, we can able to do the rotations also. When we will go for the rotation means, okay, whenever any kind of the basic operation, the insertion or deletion is happening, okay, you have to check whether the tree is in some kind of the balance mode with the formula of the balance factor. Okay, if there is no correct kind of the balance factor is there, then you have to perform the rotations. Okay, so there is four kind of the rotations are there. Okay, so one can be considered as a left rotation, another one can be considered as a right rotation, another one can be considered as a left right rotation, and another one can be considered as a right left rotation. For performing all kind of the operations, we have some kind of the running time. Okay, then the running time can be considered as a O of log n. Okay, it is a logarithmic time calculations only. Okay, so here in rotations, two operations can be considered as a single mode, another one can be considered as a double mode, which means this can be considered as a single operation, one time operation, and this can be considered as a two times operation. Okay, so here left to left, in one route only you are going to perform the operation. Here right in one route only you are going to perform the same kind of the operation, but here first you have to travel to the left, next you have to travel to the right. Here first you have to travel to the right, next you have to travel to the left. Okay, so these kind of the rotations have to be performed when any kind of the balance factor missing is happening in the tree. Okay, now we are going to see how the insertion operation is going to happen with the tree. Okay, I'm going to perform now insertion operation. Okay, so I'm going to build a tree with the values, some kind of the values, which means I'm going to insert one by one values in the insertion operation. So I'll going to perform 1 to 8 values. Okay, so first you just try to insert what is our first value to construct this tree. First we are having the 1 value. So in step 1 I was inserting the 1. Okay, every time whatever the actions that is performed in the tree, you have to calculate the balance factor. Now I have inserted one kind of the element. Now you just calculate the balance factor. Our formula is height of the left subtree minus the height of the right subtree. Okay, you just calculate. There is no any kind of the childrens are there. There is only one element is there, which means it doesn't contain any kind of the left children as well as any kind of the right children. Okay, so the balance factor can be considered as a 0. For likewise, all kind of the children last node will be there, right? For that also the balance factor can be considered as a 0. Okay, so second step, now I am trying to insert 2. Okay, so 1. So when comparing the element 1, 2 is greater. Okay, so I have to insert in the rightmost. Now I have performed one kind of the operation. So start calculating the balance factor. Okay, so the balance factor have to calculate from the bottom to the top. Okay, so now the balance factor of the 2. So 2, I have told 2 things. All the children, okay, whichever doesn't have any kind of the further children, that the balance factor can be considered directly as a 0. So here it can be considered as a 0. Now calculate the balance factor for the 1. Okay, so balance factor for the 1, it doesn't have any kind of the left children, it contains only the right children. So the height of the left subtree equal to 0, the height of the right subtree is equal to 1. So it can be considered as a 0 minus 1 equal to minus 1. Okay, so what I have said, if the value is 0, 1 or minus 1, then it can, the conditions can be considered as a satisfied condition. Okay, we don't need to perform any kind of the rotation. When we are getting any kind of the other values more than 0, 1 or minus 1, then only we have to perform the rotations. Okay, now I am trying to insert the next element. Next element insertion is 3. Okay, so how I am inserting means 1, already 2 is here. Okay, 3 is greater than 1, so I am coming to the right hand side. Then it is greater than 2, so I was inserting in the rightmost end. Okay, now start calculating the balance factor. So the balance factor for 3 is, as it is a children, it is a 0. Here 2, there is no any kind of the left subtree, it contains only the right subtree. So 0 minus 1, it can be considered as a minus 1. Here for the balance factor for the 1, it doesn't contain any kind of the left subtree, it contains only right. So 0 minus 2, so it contains the value minus 2. Okay, so as we already know the conditions, whenever we are getting the value 0, 1, minus 1 only, the condition is satisfied. Okay, whenever we are getting more than any other kind of the value, we have to stop performing any kind of the action, we have to perform the rotation. Okay, so now the balance factor is missing here, so we are going to perform the rotation here. Okay, how it can be rotated, the value is balance factor is missing here only, so I was moving towards that to left direction. Okay, so one node is coming down, so it can be considered as chain action. Okay, now 2 become parent, 1 become children, and 3 become children. Okay, so one kind of the rotation I have performed. Okay, now again start calculating the balance factor. Okay, so here 0, 0 as it is a children. So here height of left subtree minus right subtree. So 1 minus 1 it can be considered as a 0. Okay. Now all conditions were satisfied. Okay. Then again start inserting the 4. Already the tree is like this. So 4 is greater than 2, greater than 3. So I can insert here. Okay. So here what I can able to do means now calculate the balance factor. Okay. So it is last children. So it can be calculated as 0. Here also 0. Here 3. It doesn't have any kind of the left child. It contains only right child. So 0 minus 1 it can be considered as a minus 1. For the 2 it contains left children 1 and right children's 2. Okay. So 1 minus 2 it can be considered as a minus 1. Okay. So we are having satisfied condition, which means 0 minus 1 minus 1 and 0. Okay. So this is also can be considered as a satisfied. We can go for inserting the next element. Okay. Now start inserting the 5. Okay. So 5 can be inserted like this. 2, 1, 3, 4, 5. Okay. So here like this only I can able to insert the 5 as it is a greater than 2, greater than 3, greater than 4 and we are inserting in the rightmost corner of the tree. Okay. So now as we are calculating that the balance factor for children it is a 0. For 4 you calculate there is no left child, only right child. So it can be considered as a minus 1. For 3 you just consider there is no left child, only the right child. Okay. So it can be considered as a minus 2. Okay. But here the balance factor is missing. Okay. So here itself in 3, what I have said, whenever you are going to calculate the balance factor, you have to go from the bottom to the top. Okay. So here the balance factor is missing. How it can be overcome means now you have to perform the rotations again. So our tree is like this 2, 1. Okay. Our balance factor is missing here only. Okay. So you have to perform the rotation. Okay. So just pull that one element. So 4 on the top. Make the 2 as a child of the 4. Okay. Now I have performed the rotation only for this because here only it was missing, right? Okay. So I have performed the rotation only for this region. Okay. Now again start calculating the balance factor. Children's are 0. Now for height of left subtree minus height of right subtree. So it is 0. Again for 2, 1 minus 2. So it can be considered as a minus 1. Okay. Now all conditions were again satisfied. Okay. Now start inserting the 6. Okay. Now start calculating the balance factor. Okay. So here it will be 0, here it will be 0, here it will be 0. Okay. For 5 it can be considered as a minus 1 because there is no left child, only right child. Okay. For 4 if you are calculating 1 minus 2 it can be considered as a minus 1. Okay. Again if you are calculating for the 2, if there is left child is 1 and but right child is height is 3, so 1 minus 3 it can be considered as a minus 2. Okay. So here the balance factor is missing. Okay. So again you have to perform the rotation. Okay. So but previously whatever the rotations we are performing, it is in the same direction. Here it was missing in the same direction, here it was missing in the same direction. Okay. But here some kind of the changes were there. Okay. How it can be performed means, okay, it is 3. Now just to perform the rotation, how the performance rotation can be performed means, okay, here only it was missing. Just to make the 4 in the up, write the remaining elements as it is. Okay. So now 4 was followed by 5. Next 5 was followed by 6. Okay. Next 4 is again forwarded element is 2. Bring the element 2 here. Then 1 is again. Okay. Now here the 3 is there. Here the 3 is followed by the 4. Okay. Which means the 3 is the children of the 4. Okay. 4 is here. Here there is no vacant. Again come here. Just to check. To compare the 3 element with the 2. It is a greater. So you can able to insert here. Okay. So likewise, if there is a direction change, rotation is there, means you have to perform the rotation, which means you just bring the forwarded elements and the backward elements first. Okay, then you just check the space for the wherever the element is missing. Okay, then you can able to insert in the very most forwarded element will be there, right? Wherever the space is there, you have to insert that element. Okay, now just to calculate the balance factor, here it can be 0 0 0. Okay, again here it is -1, here it is 0. Here if it is calculating, I think height, it can be considered as a 2, it can be considered as a 2, so it is 0. Again, if you are inserting 7, start inserting 7, 4, 2, 5, 1, 3, 6. Okay, I think 7, if you are trying to insert, it will be comparing 4, it will be greater, comparing 5, it is greater, comparing 6, it is greater, so it will come here. Okay, how the rotation should be happened here means, now if you are calculating balance factor, here -1, here -2. Okay, here itself the balance factor is missing. Okay, start performing the rotation. Okay, how the tree will be means 4, 2, 1, 3. Okay, wherever it is the balance factor is not affecting, which means wherever it is doesn't check, you just keep the tree as it is. Okay, now wherever you are performing rotations alone, you just go. Okay, now what we have to do, you have to bring the 6 on the top. Okay, then followed by 7. Okay, now bring the 5 as a children of the 6. Okay, now 0 0 0 0 0 0 0, I think balance factor. Okay, so likewise we can able to insert the 7, and the last element we have to perform 8. Okay, so if we start inserting in the 8, okay, here I think 8 can be compared with the parent 4, it is greater, come to the right side. Then it can be compared with the 6, it is greater, again come to the 7, it is compared to the 7, it is greater, so I can able to insert 8 here. Okay, still if you are checking, the balance factor won't be missed. Likewise, you can able to insert any kind of the elements and you can able to check. Okay, so the thing is, what we have to keep it in the mind, whenever we are performing, this is an example of the insertion operation. Okay, so likewise, if I'm performing deletion operation, for example, I'm deleting 8. Okay, so just after deleting the 8, you just check balance factor is correct or not. Likewise, whenever you're performing either insertion operation or deletion operation, you have to check the balance factor is under the condition of the value 0, 1 and -1. Okay, if it contains any kind of the any other values, then you have to perform the rotation. Okay, so this is the overall concepts I can able to narrate about the AVL trees. Okay, when coming to the applications, this is one kind of the real-time application. It can be used in networking purpose, for arranging the data's purpose. Okay, and many real-time examples we can able to relate to the AVL tree. Okay, as it is a balanced self-binary search tree. Okay, it can keep the data in some kind of the balanced way, and it can be implemented in a many real-time applications also. Okay, thank you.